On the morning of December 11, 2005, Hertfordshire, England was shaken by a massive explosion at the Buncefield oil depot. The blast, measuring 2.4 on the Richter scale, was heard as far as France and the Netherlands. Fires raged for nearly 5 days, making it one of the UK's most severe industrial disasters since World War II. The explosion began when tank 912 overfilled due to a sensor failure that released petrol that vaporized and formed a flammable cloud. At 6:01 a.m., the cloud ignited, triggering a chain reaction of blasts involving over 20 tanks. Over 40 people were injured, 2,000 evacuated, and buildings up to 10 kilometers away were damaged. Toxic smoke polluted the air, while PFOS-based firefighting foam contaminated the soil and water. With over £1 billion in damages and major disruptions to fuel and industry, Buncefield explosion stands as a powerful example of what happens when safety systems fail in high-risk environments.
Next, we move on to the technical or engineering issues for this incident. Firstly, the automated tank gauging system failed, giving static readings for hours, and there was also no functional high-level alarm or shut-off system, allowing fuel to overflow. Additionally, the design of tank 912, which includes open vents and wind girders, caused aerosolized fuel droplets, forming a dense vapor cloud that intensified the explosion. Secondly, the layout of the tank farm made matters worse. It was highly congested with tanks, buildings, and vegetation packed tightly. This caused high turbulence, which increased flame propagation speed, while confined spaces intensified the blast pressure. Then, by relating to the Engineers Act, this situation violates the Section 24A until C, as this section highlights public safety, and this incident shows that the engineer failed in doing so. According to Section 15, the responsible engineers could face disciplinary action, including fines or deregistration. This reminds us as engineers we carry a serious duty to prioritize safety and uphold ethical standards at all times.
Moving on, I will briefly highlight the ethical failures behind the Buncefield oil depot explosion in December 2005, which was a disaster not just of technical oversight but of professional engineering misconduct. Under the Malaysian Registration of Engineers Act 1967 and Engineers Regulation 1990, engineers have a duty to prioritize public safety, act with diligence, communicate ethically, accept accountability, and demonstrate leadership. At Buncefield, these duties were clearly violated. Firstly, public safety was neglected. Tank 912 had a non-40 level gauge and its high-level switch was disabled, yet the fuel was still continually pumped into it. This led to overfilling and a flammable vapor cloud. This is a direct breach of Regulation 24B of the Engineers Regulation 1990, where engineers must prioritize the health and safety of the public. Secondly, there was a lack of due diligence. Despite non-instrumentation fault, no repairs or escalation were made. Backup safety systems were missing. This violates Regulation 24A of the Engineers Regulation, which requires engineers to carry out their duty with care and competence. Other than that, there was a breakdown in ethical communication. Critical failures were not reported to supervisors and safety concerns were not escalated. Regulation 23 of Engineers Regulation emphasized ethical conduct and maintaining the profession's reputation. In high-risk sectors, silence can be as dangerous as failure. The next failure is the lack of accountability. Despite similar past incidents globally, no lessons were applied. It was worse that after the explosion, many claimed it was unforeseeable. Section 15(1)(b) and (g) of the Registration of Engineers Act holds engineers accountable if their action harm public interest or breach regulations. Thusly, there was no ethical leadership. The passive safety culture allowed unsafe operation to continue unchallenged. Section 4(1)(f) of the Act reminds us that engineers must promote ethical conduct and lead by example, especially in complex environments.
For recommendations, the Buncefield explosion teaches us that technical failures and ethical lapses can have catastrophic consequences. So, several recommendations are proposed to prevent similar incidents, emphasizing the role of engineers in safeguarding public safety and the environment, as mandated under the Malaysian Registration of Engineers Act 1967 and the Engineers Regulations 1990. The first recommendation is that engineers must strengthen safety systems through redundant alarms and routine inspections. Then, a proactive safety culture is essential, addressing even rare but high-impact risks. The third one is that clear communication protocols to ensure that hazards are reported and escalated effectively. Other than that, environmental safeguards are also crucial, especially in avoiding pollutants like PFOS. Finally, regular training and strict audits to uphold accountability. So together, these measures reinforce the responsibility of engineers to protect lives, the environment, and the public trust.
Conclusion: the Buncefield oil depot explosion was not just a, it was not just an unfortunate accident; it was a preventable disaster. While the immediate cause was technical equipment failure, and the deeper issue was a breakdown in professional ethics, pure safety management, and failure to uphold basic engineering responsibilities. In Malaysia, this action would directly violate regulations A, B, and C of the Registration of Engineers Regulations, which require engineers to act with diligence, protect public safety, and minimize harm to the environment. These duties were clearly breached by the engineers. The consequences were so massive, over 1 billion in damage, long-term environmental pollution, disruption to major industries, and serious harm to public trust. This show how bad engineering decision can cascade into a nationwide crisis. That's why it's important for engineers to not only focus on the technical solutions, but also to take actions on ethical responsibility seriously. A strong safety culture, clear communication, and proactive risk management must be part of every engineering practice. Okay, that's all from me. Thank you.